Hello and welcome to your office hours. Minimal announcements this week. October 1st, Project 1, the Polygon robot is due. Most of the questions this office hour are about that project. If you're already done, you can work on the search and PID lessons. And you might notice that on Piazza in a pinned post, we've posted a preview of the next mini project, the PID mini project. It is a mini project. It'll probably be easier for you than the Runaway Robot mini project. It's just to give you some experience implementing a PID. October 16th on Tuesday at 7:30 p.m. instead of 8:30 p.m. Sebastian will be having an office hour, and I'll be posting a standard place to post questions on Piazza for that. Okay, let's go to the questions. So, first question. Um, there are several opportunities to build more feedback into a particle filter that aren't necessarily mentioned in lessons. For example, improving estimating of some parameters that were gathered outside of the particle filter, or building in a reset when particles are trending away from the target. Can I talk about these? And then a follow-up is when I make a particle filter that's truly random, it doesn't really converge well. If I try to control some of the parameters based on known things, it works better, but it's kind of cheating the purpose of a particle filter. So how should you do a particle filter? Well, you're not required to do a particle filter for this assignment. You can use other systems. And if you do a particle filter, you're not required to make a pure particle filter. So in a true, pure, ideal particle filter, you would randomly scatter your particles throughout the entire parameter space. And so generally you have kind of the X and Y location of the robot, which way it's heading, the turn angle it makes, the number of line segments it does before it does a turn. And, you have all of these parameters. And, that's a pretty big space. It's 5, 6 dimensional space. And so some of these are integers, and so it's maybe 16 possible values, and so that's not too big. But a lot of them are floating point values that are a continuous range, and it can be pretty much anywhere in that continuous range. So if you do that, you're going to find that you're going to need a lot of particles to effectively cover that space. And effectively, assuming your particle filter is coded right and implemented correctly, most of those particles will be immediately dropped and not resampled. As soon as we find one XY location from the robot, it collapses this giant search space down into a much, much smaller search space because the X and the Y are almost completely fixed. I mean, obviously they're within a couple of units, but there's a big world, and we know the robot is pretty close to right here. And then as you move around, you can start ruling out certain turn angles and certain headings pretty quickly. If the robot's going this way, the heading that way doesn't work. Um, so a lot of people say, well, let's just short circuit all that beginning bit and take 3 or 4 measurements, get an estimate for where the robot is, what direction it's heading, maybe estimate the distance it's moving each turn, maybe get an estimate on turn angle if we see a turn. Um, and we can, instead of just scattering particles randomly throughout this parameter space, we can put the particles very close to where we think the robot particles or the robot parameters are. And that makes a lot of sense. You can use less particles, you can more intelligently lay them out. And so after you do that, you can just let the particles take off, and use the particle filter as it's supposed to be used. And so one thing to point out here is that most particle filters, when they resample, will perturb or add a little bit of randomness to the parameters. And the idea here is that some of these resampled particles will be closer to the actual parameters, and some of them will be farther away. The ones that are farther away will veer away and gradually get farther and farther away from the measurements, where the ones that are closer will stay close to the measurements. And ideally, your resampling, your importance weighting algorithm and your resampling system will gradually drop out the ones that are moving farther away and gradually reinforce and keep the ones where the parameters are getting closer. So in any particular 1D parameter space like a number line, you have measurements that are coming in, and then well, if you have X and Y, you have measurements coming in, and so your robot should be getting closer to those measurements. Now, some of the parameters are not directly observable. So, the heading isn't directly observable from your measurements unless you take 2 of them together. And since the 2 endpoints have some noise, the heading isn't perfect there. But over time, particles with the wrong heading are going to diverge from the robot actual measurements. And so they should stop being resampled as they get farther and farther away. So sometimes if your particle filter isn't working or tuned correctly, things really start to diverge. And a lot of times this can be fixed by tuning how the particle filter is doing the importance weighting and the resampling. So if you have your particles that kind of are near where the robot are and then they really diverge quickly, it might be that you're adding too much random noise. And one trick you can do is the amount of random noise you add should get smaller over time. You can think of this as simulated annealing. But as your parameters are getting closer and closer to the actual robot parameters, if you add too much random noise, you're going to kick it away and it's going to be way too far away. So you want to add the right amount of random noise so that it's likely to get closer, but not overshoot in one direction or the other. And as your parameter space is really big and your particles are scattered all over the place, you want the changes to be kind of big. But as they get closer and closer to the actual robot, you want those changes to be smaller. So you could do something with over time, you gradually reduce it. You could say, hey, what's the size of my cluster? As the cluster gets bigger, I do more. As the cluster gets smaller, I do less. There's different things you can do with that. So if you're looking at things and they're diverging, you might consider tuning how your particle filter is adding noise and how your particle filter is resampling before you look to external estimators. Now, if you have an external estimator and it's dead accurate and it works perfectly, there's no need for a particle filter. If you're able to say, yes, it is every 12 moves it's going to turn, and that's right, well, just set all your particles to 12 and be done with it, because obviously you've come up with an estimator that's better at that particular task than your particle filter is. Just keep in mind that if you're wrong, you screw up everything. The nice thing about a particle filter is you might have 99 particles that are at 12, but every so often, one out of 100 resamples, you move that 12 to a 13 or to a 11, and maybe that one particle just suddenly starts predicting better, and it turns out, oh, it is an 11 and not a 12. And so that's where the particle filter, the ability to maintain multiple hypotheses of what is this parameter, an integer parameter, it's either 11, 12, or 13, that type of thing. So you are not required to implement a pure particle filter. You can do hybrids and tricks and reset the particles if you think it's getting out of whack. And some of those things will solve your problems. However, many of those things could probably be avoided if you kind of tuned the importance weighting and the random noise that you're putting in there. And keep in mind that the amount of random noise you want to add might change over time as your particle filter kind of coalesces down and gets closer and closer to the actual parameters. Okay, next question. In a particular problem set 3, video 6, the particle filter function took a list of several previous motions and measurements. So it used these lists of motions and measurements, and then it calculated, some output. So in project 1, it seems more natural to pass only the current measurement rather than a list of measurements. What are the pros and cons of these methods? What's the difference between doing a list of measurements versus one measurement at a time? So I want to add some vocabulary, and my vocabulary here is the difference between online systems and offline systems. So an online system works as data arrives. So you get reading from your LiDAR sensor, you get reading from your ultrasonic sensor, you get, whatever sensor you're looking at, you get reading from it. And then you have to make a prediction of where the target is. You have to make a decision of what your robot's going to do. Are you going to move your arm? What are you going to do? And so in an online system, it has access to all the previous data, assuming you've been saving it, and it basically gets the current data, and then it makes a decision about what it's going to do, or an estimate of what the parameters of the system it's modeling are, or the location of whatever it's tracking, and so forth. And then a new set of data comes in, and it makes a new estimate. So the key difference here is that an online system can look in the past because it has all that data presumably stored up, but it can't look in the future. Now, in an offline system, you're given a dump of data. And so maybe the Google car has been driving around all day. It comes back to the garage and uploads, here's all the things I saw. So Google will take all this data, send it off to a cloud, and they'll use neural networks to start looking for stop signs and, speed limit signs and this type of thing. And maybe they had a person riding in the car that would say things in a dictaphone like 3 lanes, left lane turning left, right lane, must turn right, center lane must go straight. And their neural network is maybe they're having somebody key that data in, maybe they have some voice system that automatically keys it in, but their neural network is being trained to say, spot these signs, spot these road markings, and tell us what they are. And so they can train these neural networks based on the whole day's worth of data, or in this case, months of data that they've collected, and they can go back and train them again and test them again against the old data and see how they're doing. And so they're producing, a newly trained neural network that's very good at identifying a particular type of sign, like this neural network identifies stop signs. So their offline system is used to generate a neural network that is then ran on a GPU or something, hardware acceleration, in the car. So their offline system looks at all the data they've collected and uses that to improve the results. Now, let's talk about your problem set first of all. So your problem set, although it gave you all the data, it was really running through it with a for loop from the beginning to the end. And so it was really kind of being just a simple way to say, here's how I'm going to give you a list of data. We're going to call your function and it's going to process it with a loop, and go through. So realistically, that problem set was looking at the data in a online way, and that it was kind of starting at the beginning and moving forward and generating something at each step. A true online system, you'd give them the chunk of data, and then they would generate, for example, an estimate of where the object was at each time step, but they could go forward and backwards through the data. So they could say, hey, at this time step, the measurement was here, and then the time step after it, the measurement was here, and the time step before it, the measurement was here. So maybe, if you draw a straight line, this one in the middle is off. So maybe I should move this middle one in a little more based on what came before it and what came after it. So an online system would say, hey, there's a line going this way. So, it's moving down, or it's moving off of this line and it's moving down, but it wouldn't be able to look at the next time step to say, oh, it moved back. So this is an anomalous reading. So, an online system would say, oh, it's going this way, where an offline system would look at all the data and see this long line of data with one point off and say, well, I'm just going to move that point a lot back in. Um, so the main difference here is that the online system processes data as it comes in, and it gives you information based on all of the previous data and the current data, but it can't look ahead. Whereas an offline system can look at all of the data and just go back and say, well, I'm going to change my estimate for that beginning point because of all this stuff I've learned from all the other data. Um, so my point here is that in the problem set, they're giving you all the data up front, but you're solving and using it kind of in an online system, kind of like in the Project One or the Runaway Robot mini project. So in the mini project and Project One, we are specifically calling your function once with a new piece of data, and every time we call the function, you get a new piece of data. It's up to you to store the data. So if you want to use the old data, you can store a running average. You can actually just have a list of all the previous data and then go through it and do whatever you want with it. But we're doing that because this is more typical of what happens in an actual robotic system. The robot gets some sensor data and it has to make a decision about where it thinks the target is, what it's going to do, and so forth. And it has to do that before it gets the rest of the data. All right, so I've talked about that long enough. Let's move on to the next question. Okay. A lot of students are having trouble with part 4 of project 1. So part 1 is solve it with geometry, there's no noise. Part 2 is basically, hey, you get some measurements, figure out where the robot is, but you're not actually trying to track it down. Part 3 says, hey, given a hunter robot location, you tell the hunter where to go so that it can catch up with this robot. And basically, if you have part 2 working, part 3 is pretty easy. You just say, go to that point, because your robot is actually faster than the runaway robot. So you can basically just track it down and be jumping on top of it all the time. Part 4, the main difficulty there is your hunter is slightly slower than the runaway robot. And so what this means is you cannot catch up to the runaway robot if you go to its position every time. Luckily, the runaway robot's going kind of in a circular path, or at least a regular polygon path. And so you can cut the corner. If there's a curve, you can go from here straight across there, and you can get there faster than the runaway robot who's going around the outside. So the only thing you really have to do is project ahead more than one step. So parts one, two, and three, you really only need to project ahead one step. Whereas part four, you need to be able to say, hey, there's one, two, three, four, 5 steps ahead. That's the first place I can go in a straight line and meet it at the same time. So you need to be able to project ahead n steps where n gets bigger, however, if it's a very a long line needed to cut that curve off because it's a not a very sharp curve. If it's a very sharp curve, it's less steps. And one thing you might notice is that you get fewer chances at catching up to the robot. So in parts two, every time you get a measurement, you get to make a guess of where the robot is. And if you get it right at any point, the game is over. So it doesn't matter if it takes you 200 or 500 tries because you're getting 1,000 tries. And so as long as you do it in less than 1,000, you get full credit. Now, in part three, it's basically the same thing. You might start somewhere different from the one array robot. So the first 20 moves might be getting to kind of catch up to it. But after that, it's only moving and you're moving right with it. And so you're trying to jump on top of it all the way around. And so you get, 900 or so tries to catch it. And so you might have an estimator that solves the problem 1 out of 50 times, or, gets close enough 1 out of 50 times. But if you get 300 tries, well, if after the 50th time, you got it and you're done. So in part four, you get less tries because more of your movements are not getting up to the robot. They're cutting off they're straight lining across a circle. And so you might get, every 5 times or every 20 times, you actually are close enough to the robot to try to jump on it. And so if out of that you need 50 times 20, that's getting to be a big number, and you might not get that in 1,000 steps. So if your part two isn't solving it in 50 or 100 steps, you probably want to improve your estimator, your location estimator in part two, and try to get that better. Um, and that'll help things in part four. Now, in part four, the conception here isn't hard. I mean, you just project ahead a couple of steps, and then you go to that point, and you basically just have to figure out, how far do I need to go, and how far will this other robot go, and can I do that with my speed? And if you can't, you project forward steps until you can do it. So, running a particle filter multiple times, or running a Kalman filter multiple times, hopefully you can project ahead more than one step. Just keep in mind that you want to update your particle filter back where it was, so you might need to diverge, make a copy of your particle filter that you're moving forward 10 times, and then keep the original one for the next actual motion update. Another hint is that you project forward 10 steps and you head for that position, but as you get closer, you can improve your estimate by looking at where's it going to be one step ahead now. So when you're 9 steps in, look at where it's going to be one step ahead, and that's probably going to be better than your estimate that was 10 steps ahead. So you can improve your position as you get closer and use the most accurate, most up to date estimate you have. But I do recommend that you visualize your tracking hunting robot, and I recommend that you modify the testing suite to print out how far away, what's the actual error between your hunter and the target, and make sure that number gets smaller and smaller and smaller. And so that's the two pieces of information you really need: is visualize your hunter and its location and make sure it's looking where it's going and doing the right thing. And pay attention to, are you one step ahead or one step behind? Because it's pretty easy to be an off by one error where you're always jumping exactly one step behind the robot, or you're jumping one step ahead of the robot. And so your error is kind of close, but not anywhere near close enough to get credit. And so, watch out for that type of thing. But essentially, the estimator and your location estimator are key, and they do need to work better for part four than it does need for part three and part two. So just because you've solved part three and part two in 800 steps doesn't mean your estimator is good enough for part four. All right, let me reload here and see if there's any new questions. All right, no new questions. I will see you next week. All right, goodbye.